We're going to talk about some concepts behind voxels this particular lesson. And we're going to talk about it using some non-technical methods at first, and then we're going to jump inside of the Houdini interface and start looking at some specifics inside the interface. But keep in mind that when we're in the interface, we're not going to be talking or teaching specifically like right-click on this and then do that. It's way more about the idea behind what's happening. So don't be so concerned about like writing down every single note or every single, oh, then he right-clicked on the green button. Like that's not necessarily what we're after here. What we're after is a fundamental understanding of what's actually happening in the software. Now, I'm going to probably do about 20, 30 minutes worth of my pre-built presentation. And then the really good part of this and what we've been doing is to open it up to the crowd, and you guys get a chance then to ask questions. And don't be afraid. Just ask anything that you want to ask, and if I can help you, we'll dig into it and we'll get into it. If we can't, I'll try to get you somebody that can. But that's kind of how we're going to run today for this particular session. Hi, I'm John Moncrief. I work at a company called Pluralsight. We were formerly Digital Tutors, and we were acquired by a much larger company called Pluralsight. Pluralsight offers IT, tech, and development video-based online training, and we were sort of their creative library now. So we now handle all of their creative stuff for creative design and engineering software. Things like AutoCAD, SolidWorks, all of that. Today we're here to celebrate the creative industry and the creative elements, specifically through Houdini. So there's me. If you have any questions, you can definitely feel free to write down my email or come get it later. If we don't get to something, get a hold of me that way. It'll be great. Okay, so let's start to talk about voxels and what a voxel is. Now, a voxel is really just a three-dimensional pixel. Okay, so you're used to working in Photoshop and you're used to seeing pixels. Well, a voxel is just a three-dimensional version of that exact same concept. And we're going to break it down a little bit further here in a minute. But really, voxels, the two major areas that you're going to be working, where you're going to have to deal with voxels and understand what a voxel is and how it impacts what you're doing, are going to be when you're working with fluids. Houdini currently really has, now keep in mind this is an overview. Any of you that are like TDs and you're like, oh, there's way more fluid types. There are, I know. But like what we're going to discuss is specifically voxel-based fluids, which are used for things like fire, flames, the pyro tool set that Houdini has. And then there's also flip fluids. Now, flip fluids are basically a combination of a particle-based system and a voxel-based system. So really, if you're going to work with either of these two elements inside of Houdini, having a solid understanding of the concepts of voxels and how they work is fundamental. So let's talk about how voxels actually work. So voxels really are just little pieces of data. They're three-dimensional pixels. We said that, but let's stop and think about this in a much more simple way. We can think about it, like you would an Excel spreadsheet, okay? So you have this Excel spreadsheet, and in this Excel spreadsheet, you have these little boxes, right? We call them cells in Excel, and each of these little cells has a particular value. This particular value here is 0.895, 0.54, and 0.375. So that's a particular cell inside of this spreadsheet that has a value. It defines, in this case, a color. So the color in R, G, and B values would be a 0.895 in red, 0.54 in blue, and 0.375 in green. We could say that is a spreadsheet that defines color for those individual cells. Well, we can also have multiple pieces of, multiple collections of data within that spreadsheet. Excel calls them sheets, right? So we have one sheet that defines the color. We have another sheet that defines, say in this case, viscosity. We have another one that would define velocity, right? Now, in Excel world, these would probably be like my taxes, I don't know, the water bill, and something else, right? But they're all just little pieces of information that are collected inside of this thing that we call a sheet inside of a spreadsheet. Cells of data in a sheet that are inside of a spreadsheet, right? So pretty familiar concept. We all know Excel. Move on to the good stuff. Here we go. So The good stuff. Well, we need to think about voxels the same way that we do pixels. In Photoshop, if you have a particular pixel, you know that that pixel has a color, an RGB value. Much like when we looked at our spreadsheet, that cell that we looked at had a particular value to it, right? An RG and B value in that cell. Well, a pixel can have the same thing. However, if you're going to start to define shapes inside of Photoshop, you know that if you have 4 pixels, about all you can make is a box, and that's about it. Well, this is kind of a little example, a little breakdown to talk about resolution of voxels. And we're going to start in a 2-dimensional world. So we want to think about this. Let me change my interface up just a little here. So we want to think about how these divisions are made. You can see here as I change the number of divisions in this grid. Think about this, like I said, as you would a 2-dimensional picture in Photoshop. And each of these little boxes that makes up these rows and columns are how you would think about your pixels. And what we want to do is we want to basically make a picture of this red circle. That's our goal, is to try to make this red circle. Well, the problem is if we don't have enough pixels, we end up with something that looks like a square. Now, of course, we can add more pixels, right? And the more pixels that we add, the more and more that our shape begins to look like we want it to. The more and more that it begins to actually look like a circle. The thing is the more of those little pixels that you add, the more divisions that you add, the more definition that you give to that circle, the longer it takes the computer to calculate. Now, in this particular case, this is a piece of cake for most modern computers. It's not that big a deal. The problem is that this is a 2-dimensional example. This is pixels, right? This is 2D. We talked about how voxels are 3D pixels. So this is kind of the same thing. You're like, well, that looks about the same. But now we break it off into the 3-dimensional world. Okay? So this is like a 3-dimensional spreadsheet of data. What we've got are these boxes that run not in just X and not in just Y, but also in Z. So we now have 3 dimensions of information that we're storing on this grid. You say, all right, well, that looks pretty cool. Let's see exactly here. This is the voxel grid that's defining that sphere. This is all the information that we can possibly store about that sphere is in this set of little tiny boxes. This set of little tiny boxes is the equivalent to a single sheet in Excel. They're just little cells that hold information, okay? Now, if we look at what our sphere looks like, this is our source sphere. This is our goal. This is what we want to be able to visualize using voxels, okay? We want to represent this 3-dimensional shape in voxel space. Well, right now with the resolution that we have, this is about the best that we can get. As we start adding more and more definition to our scene, we see, okay, all right, our voxel grid is now starting to better represent exactly what we want in voxel space. And you think, oh, that's great. All you need to do is pump up the resolution. That'll make things look exactly like I want without any problems. Well, the big problem is now, this is your voxel grid, right? So you're dealing with this many containers of information trying to define exactly what that sphere looks like. They're 3-dimensional pixels. So before I get too much further along, does that concept click? Does that make sense? Are there questions about that? Because I'm happy to answer anything at this point, kind of about what a voxel is and how it works. All right. Cool. So that's what a voxel... Oh, yes, sir. No, the question was basically, do voxels move? How does information in a voxel grid, does it move? Do the voxel boxes themselves move in the grid? Is that correct? Am I kind of understanding? No, that is the voxels themselves do not move. Once you sort of define that grid, you're saying here's a container in 3-dimensional space, and I want to be able to store information inside of that container. What moves is the information, okay? So let's think about this in Excel terms, just to take it back a step, okay? So right now, we're looking at this, and let's talk about color. Let's forget about these other two here, velocity and viscosity, for a second. Let's just think about color, a single sheet, a single voxel grid. I've got these cells. They're in 11 rows by 3 rows, rows A, B, and C here, and all the way through 11. And each one of them currently has a value in it. So if we were looking at this in a pixel representation, we would see color in every single pixel. Thing is I can do this. Right? The equivalent in three-dimensional space of this, meaning I have voxels that do not have color information in them. In this case, I have cells that do not have data in them. So there's no information there. But there's still a cell. There's still a cell there. It just doesn't have any information in it right now. So if we look at it back in the 3D world and we think about this, let's take these divisions down to something a little more simple here. I'm going to see both of these, right? So what I've got here is I've got this voxel in the middle. Think of that like you would that cell in Excel. It currently has information in it. Now, we're not going to break it down into the different pieces of information just yet, but it has information in it. Okay? You could think about it if you wanted to as it has surface information in it. I need to create a surface of something in this box. We have given that particular voxel information to put something in that placeholder. These others do not have any information in them. Okay? Now, when you think about when a fluid moves throughout the box, you're like, well, if it doesn't move, if the voxels don't move, how does the sphere get represented in different places? The information is what moves through that grid. So, in other words, I can take this 0.65, 0.25, 0.87, and I can hope my keyboard works. I can move that over here to this piece of information, right? I'll just paste. So now I've taken that data from this cell and put it over here in this cell. If you were looking at that, what you would see is you would see that red block in 3D voxel space would be in one spot. In the next frame or subframe or whatever, the next piece of the timeline, that would now be empty, and that red box would have moved over into a different voxel. But the cell itself did not move. The voxel itself does not move. The information inside of it just shifted over to the next cell over, to the next voxel over. Does that make sense? So that's how you can get, that's how motion, it's basically just pushing data. You're pushing numbers and information and data through the grid. The three-dimensional grid, the three-dimensional voxel grid. So that's this guy. Let me see, I never do this. I'm gonna go off script for just a second, and I'm gonna see if this is gonna work. Please don't worry about the actual grid setup here and how this is done. I wanna see if this will prove the point. I wasn't expecting that question, but I think this is gonna prove it pretty clearly, not English words. Okay. So all I'm going to do is I'm going to try to move that sphere throughout our voxel grid. Oh, that's the grid. This is why you don't go off script in a live demo. Just so you know. Ever. Don't go off script, ever. We will see, in just a second, I have another example that I think will address that a little better. We're actually going to create voxel space, and we're going to kind of move some stuff through it, and you'll be able to see that a little bit better. So, but does that answer the question as far as how stuff moves through the grid? The grid does not move. Data just moves through the grid. Okay, awesome. Okay, were you in the class earlier when we talked about attributes? Okay, it's very much the same idea. Points, we looked at points and point attributes, and points can have color, a CD attribute. Well, points could also have a position attribute. We saw that too, right? We had a P and also a CD. Both of those things were on that point. Voxels work sort of the same way. So this particular setup that we're looking at here, like I said, let's think about it as surface. We have that sphere that's represented in the voxel space, and if there's enough resolution, you say this voxel needs to represent the surface of the sphere. Well, there's also other pieces of information, just like you can have different attributes on points, you can have different fields is what they're called, or pieces of information inside that voxel grid. Color could be one, velocity could be one, surface could be one. So all of those are called fields. Much like in Excel, these are called sheets. So this is a sheet that represents the color information, a sheet that represents the viscosity information. In three-dimensional space, the word for that is grids. Okay, so you can think of the voxel grid sort of like you would as an attribute. If you're trying to like make a comparison between the two, you say points have attributes of position and color and avocado. We made that one, right? You can have a voxel grid that has surface and velocity and avocado if you wanted. It's just a different way of calculating that information and thinking about how that information is processed. This is voxels instead of points. Questions? Other questions? Anybody while we're here? Yes. A grid is a collection of voxels. Think about it that way. In the same way that in Excel, you would say a sheet is a collection of cells. So these are all Excel cells, and they're on a sheet called velocity. Over here on this color sheet, I have different information in these cells. In 3D space, the terminology for that same equivalent is, think about this as the cell. One of these little boxes is a cell. Okay, that's a voxel. And then the information that you have here that we're saying is surface, the surface of that sphere, that surface would be the surface grid, if you will, or field. Grid's a horrible way to put that. Let's use fields. Let's make it solid because that's the correct Houdini terminology. It's a field. The grid is just something you say of a collection of voxels. That's a voxel grid because there's a bunch of voxels. The information, the surface information that represents what that sphere is the surface field. Okay. There's also the idea that you can have, well here, let's just get in, does that help at all? A little bit? Yeah? The question was we're having a terminology question about grids, fields, and voxels and how those all go together. And basically a grid is a collection of voxels and the information in that voxel grid is called a field. That's the straightforward as I can kind of get with that one. Are there other questions? Anybody else? Does that help? I hope that helps. Okay. So we're going to talk a little bit now about dynamics, and we're going to move into the world of DOPS. Now we're still talking just about voxels and voxel fluids. So remember earlier we talked about how voxel fluids are primarily used when you're doing things like pyro, flames, smoke, that kind of thing, within Houdini specifically. So this is a very simple smoke simulation. I'm just going to go ahead and play through this here. And let's take a look at this, the smoke here. I'm going to hide and get rid of this torus that's moving through our scene here for just a second. Again, don't be too concerned about exactly where I'm clicking inside of the interface and all the nodes right now. It's more the concepts that we want to talk about. Here, I'll tell you what, let's just make one from scratch. It'll be easier that way. So I'm going to start with just a regular sphere. This is going to be the source for our smoke. This is going to be where the smoke that we create is going to exist. Now I'm going to set it up real quick here. I'm going to come over to the pyro effects shelf, and let's just make really quickly a wispy smoke out of it. Let the laptop do its thing here for just a second, and boom. We get all of these nodes and all this scary stuff. Not our concern right now. What we want to look at, though, is how it's represented visually. You can see that we have that sphere right there. Hang on a second. We're looking at too many things at once. There we go. Oh, I know what happened. Sorry, guys. Give me 1 second. Let's do this in a new Houdini setup. Sorry about that. How's everybody's SIG graph so far? All right, bravo. That's filler. That's how that works. Keeps my hands from sweating quite as much. All right, so we're going to start with a sphere, and we'll come over here to our Pyro Effects tab, and we're going to turn that into a smoke. Let the laptop do its thing, and there's our sphere. Now, if you look at how this is displayed on the screen and zoom in here a little bit, you can see on these edges, turn off that source grid just to see a little clearer, that we have this series of tick marks. That series of tick marks along the edge is what's representing the voxels in 3D space for that particular sphere. So there's our sphere, and this is representing the grid. Now, that should make sense in X, Y, and Z. We have this many divisions in X, this many divisions in Y, and this many divisions in Z. If we look back at our other scenes, this is why I needed to have two of these guys open. We'll jump back here to this example. All we've done here is we're talking about the number of voxels that are in that grid, the divisions. The more resolution that we add, we know the slower it gets to calculate and the more resolution that we have for our sphere. Well, the way that that looks inside of DOPS, inside of Dynamics, is these little tick marks up and down the edges. Okay, so you can just imagine a box that's exactly the size of one of those little tick marks, and that's a grid that you see all the way across. Now, we don't have to necessarily see that, because when we're working with our fluids, we don't really want to look at it through a grid. We want to see the motion of the fluid as it moves throughout the grid. To address your question from before, this is information, density information, and we can look at that, which we will in just a second, moving through the grid. Now, when we talked about attributes and we looked at the geometry spreadsheet and we saw how attributes were set up, they look sort of like an Excel spreadsheet. In DOPS, when you're working with dynamics, you have to go about it just a little bit different way to get there. So I'm going to go ahead and split this pane into two different areas so we can see that information again. We'll split this left-right, turn this over to the geometry spreadsheet again, and it looks a little different right at first. Okay? Well, that's because we're now into the world of dynamics. In dynamics, your spreadsheet looks a little bit different. But now we're going to readdress the question of fields and grids and how all of that comes about. We talked about velocity, and you said, well, what is velocity in that spreadsheet, and what is color and surface and all those different things? You see them here inside of the geometry spreadsheet as fields. These different little boxes here, if you zoom into the interface and look at these are the different individual voxel fields of information that you're looking at. There's a fuel field at play here. There's a density field at play here. That density field, very simply, is the exact same equivalent of our red sphere that we had in our big box of boxes. It's where is there information? Where do I have density inside of my grid? Where do I need to put smoke inside of my voxel grid? That's defined by this density field right here inside of the outline, or inside of the geometry spreadsheet. You can see information about that field over here as well. We can actually see the number of individual voxel grids. Of individual voxels within the grid. We can see the position of it. Here's the divisions of that particular box. Let's rewind our timeline back to the very beginning where we see our sphere represented here. Get a little bit of smoke in the scene. And we'll start to talk about that idea of resolution inside of a voxel grid. With the sphere, we needed more and more and more and more cubes till we got rounded edges, so we actually had something that looked like a sphere. Inside of a smoke simulation like this, where you've got density information moving through the voxel grid, to get a higher resolution smoke with those cool little wispy corners and curves and things, we have to raise the resolution of our voxel grid. And that's done here with division size. So basically what we're calculating is the space between the divisions. So if we look along our edge here, this is representing our voxel grid. We have a 0.1 distance here to represent a particular voxel. If we want to put more resolution into our grid so we can get a little bit finer looking smoke, we can rewind the timeline. We'll change this division size from 0.1 to like 0.05. So now I've made it half the size. And if you'll look at this indicator here along the left-hand side of our voxel grid, our little tick marks are much, 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 much smaller now, meaning we have a lot more voxels inside of our grid, meaning that my smoke is going to have a lot more detail. It's actually going to have these cool little wisps here that it didn't have before, but notice what happened as soon as I did that. The playback is super slow now, right? So it's chugging along. My little laptop is really trying to race to figure out exactly where it needs to move that density information throughout the voxel grid, and that's because we now have 4 times the amount of voxels that it needs to calculate. So that's a fluid moving through a voxel grid. That's basically just smoke moving up through a voxel grid. And how adjusting the resolution, you can see the impact of that resolution adjustment by making that grid just a little bit more fine to get a little bit more detail. You have to think about that in all 3 dimensions. That increases the number of voxels exponentially when you do that. It's not just a matter of saying, oh yeah, make it twice as big. When you make it twice as big, it does it in 3 dimensions, 3 different pieces of data, that many more voxels that has to be calculated, with that much more of an impact on your calculation time. I'll just, real quick, questions? Is that anybody? More questions?
The voxel grid is not spanning, correct?
Correct. Correct.
It looks like it is, but it's not.
Well, this will be a fun one to answer. This particular node right here, this resize container, is a tricky little sucker. And basically what it is doing is it's looking at where there's information and expanding the size of the container to calculate where the voxels are. Yeah, that's a tricky one. Good question. Come see me after class. The concept is, though, that you do have a predefined, preset size for your voxel grid that it cannot grow or grow out of. And you see that here if we play this out long enough, that eventually the smoke reaches the top of the voxel grid and it gets cut off. Like that smoke does not continue to exist outside of that max bounds of that voxel grid. So really that container that you're seeing here is showing you the resolution of and the density information that's inside of that particular box. So yeah, it looks like it's growing, but as soon as it hits the max size, it stops expanding. You cannot expand outside of the initial set voxel grid unless you increase the size of your voxel grid. That's one of the problems with voxel fluids, is that they're limited to that defined grid. You set off in the initial piece and you say, I want my fluid to be this big, 10 by 10 by 10, and you go and you let it run and you let it simulate. If it goes beyond those borders, you have 2 options. It can either bounce off the wall and continue inside the box, or it can just get cut off. But that's the end of it. That's the end of the fluid. It has to stay within the bounds of your box. That's one of the problems with voxel fluids. Yes, sir? The question was, can you set up initial voxel grids and have data pass from one to the other? Yes, definitely, 100%. You can easily create those fields. Again, we're using that term fields to mean a particular grid of information, like a velocity grid. Yeah, you can set up a velocity grid. You could set up an avocado grid, and you can transfer that information back and forth between the two, just like we did when we did attributes with attribute transfer. There's tools within the DOPS toolkit that will allow you to transfer information between those particular fields, to blend that information, put it into a new field, use that to drive color, use that to drive surface. It's that same procedural concept, that same procedural thinking as when we had points and attributes of fields and voxels. You're exactly right. You can push that data around anywhere that you would like. I don't have a really phenomenal example of that particular scenario right here in front of me, but again, if you want to come up and chat with me in a minute, we can kind of dig into it and go through that particular thing. Or, yeah, just come see me afterwards, but yeah, you can definitely set it up the exact same way. Well, as far as the calculation is concerned, you do have the ability to switch on. I don't know, my laptop may explode when I try this. You do have the ability to calculate OpenCL in. Let me find exactly where is that sucker. Jonathan, you may know this. Where's the OpenCL switch? Is it in the Pyro? Ah, ha, ha, ha. Thank you, sir. Good save from the audience. By the way, Jonathan is a genius. He was also a wonderful intern with me at Side Effects for a while and helped me co-create my very first course I ever did. So bravo, Jonathan's awesome. Good save, good save. Yes, you can actually implement, cross your fingers, my laptop graphics card may explode, I'm not sure. But yeah, you can definitely use OpenCL to calculate voxels and voxel grids. Yeah, it's going a little bit faster there. You can definitely see an improvement in the speed. But using OpenCL, enabling the graphics card to calculate some of that information will definitely help improve the calculation time. Ultimately, you're going to write this out to disk before you render to get an image. You're going to take this information and cache it out to disk, and then you're going to render it. So really, the OpenCL here is helping us immediately in the viewport to get a faster playback, a smoother look at when we're doing like look dev for something like this. But ultimately, you're gonna cache it all out to disk, and it's going to be dependent on all different elements of your computer as to how fast that happens, how fast your disks read and write, and all that kind of stuff. So, yes, I'm what? Yeah. I got a switch. I can slip on a little switch and NVIDIA goes, we're badass, and stuff starts to happen quicker. I'm like, thank you. Thank you so much. We're at 38 right now. I was going to go into discussing a little bit about how flip fluids work. Do you guys want to move to flip fluids for a second? All right, let's do that. So, flip fluids. Basically, let me get my little presentation back here. Flip fluids are a combination of, are we back? Come back. There we go. Nope. Doop, doop, doop. Two different types of fluid systems. Way back in former versions of Houdini and other wonderful days gone by, SPH fluids were a key for particle fluids. When the interface referred to particle fluids, you were basically creating what's called SPH fluids. All that really means is that it's fluids that are defined by little points. Okay? So we're going to leave the idea of voxels aside for just a minute. Just put that in your back pocket. Hold on to it. Now let's start talking about how we can define fluids and the look of fluids using points. We all know if we just have a piece of geometry, you can go into ZBrush or any other tool, or even within Houdini, and sculpt those points to make them look like the fluid of a surface, right? All you're doing is just moving those points around to sort of say, yeah, that looks like water. SPH fluids sort of are the same concept. You've got points that exist in space, and they are communicating with each other on how to move, and then eventually you mesh it, and you got something that looks like a liquid. Well, SPH fluids, instead of using a voxel grid that you push information through the grid, in this case, the little points or particles, as we would call them, actually do move around the scene. And they all talk to each other. They communicate to each other directly, basically like a group of little hippie backpackers going through the woods. They all have this backpack full of information that they can exchange with each other. So like, hey, I need a granola bar, I'll trade you for a beer. Like that kind of idea is exactly how like SPH fluids worked. Like any one of these individual little red dots, one of these pixels, or I'm sorry, particles, has velocity information on it, right? Just like attributes and points that we saw earlier. And that information can be exchanged with each other to figure out where they're supposed to be going inside of the scene. So it's a little bit different than pushing data through a grid like you would think of an Excel spreadsheet, but it's another way of kind of calculating how fluids work. Well, one of the problems with that is that you can't necessarily render just those little points. You have to go through and take an extra step of creating a surface for them. So you have to wrap polygons around them at some point so that you have something to render, right? Well, in order to get a really decent looking detail inside of your fluid, you need a lot of particles. So you have a lot of particles being generated so that you can get little fine details inside of your fluid surface that you're going to render. But with that many particles, oftentimes you'll have them that end up on top of each other. And when they end up on top of each other in a scene like that, they tend to explode. Literally, your mesh will just go crazy. It'll blow up in the scene, and you won't have anything that you can actually render. The behavior gets really out of control. So the problems with SPH specifically, they don't behave very well. If you want to get a nice high quality out of them, you have to turn up what's called substepping. We're not going to go into that too much, but let's just put it this way. It takes a lot longer to calculate them to get a really solid look. Okay, so they're slower to calculate when it looks good. You need a very large number of particles to get a detailed surface, which was another big problem with SPH fluids. And there is no inherent surface. You have to actually take an extra step and wrap them up in polygons in order to be able to see them when you render them. Well, along came flip fluids. And thank God for the geniuses out there in the world that figured all of this out. But flip fluids basically takes a combination of how particle fluids work, right? Little hippie backpackers talking to each other, and this idea of an Excel spreadsheet, and it kind of merges the two of them together. And it says, okay, I'm going to take those little bits of particle information, and I'm going to take the movement of them, how they move and how they move throughout the scene, and I'm going to use a voxel grid to calculate how that moves. Because the voxel grid gives us the ability to do much smoother looking fluids, but also still have all the benefits of what an SPH particle system has, right? So one of the major benefits to that, of being able to use both particle tools, one of the major benefits is being able to use two different tool sets. So you're working with particles and points, so you can go in and you can manipulate those attributes on those particles and those attributes on those points using all of the point-based tools that Houdini has to offer. We saw some of those in that first class. And you also have the ability to use all of the voxel-based tools that DOPS has to offer. Very simple things like gravity fields. So let's go ahead. I'm going to just jump in there and kind of prove that. We're going to create a quick little flip fluid, and we're going to use both voxel-based tools to affect it, and then we're also going to use some of the particle-based tools to affect it. So let's just create a new scene here. And we'll go ahead and just start with a sphere. Move it up a little bit in our scene. And I'm just going to emit some fluids from it. So the particle fluid shelf, keep in mind now, this is a little bit of a nomenclature thing. It says particle fluids. Really what it is a flip fluid. You're developing something that uses both voxels and particles when you're creating that particle fluid. So we'll go ahead and we'll emit particles from our sphere here. Let the laptop do its thing. Wonderful Houdini shelf tools makes your world so much nicer, and boom. That's being spoiled, by the way, right there. Click one button and it'll make fluids for you. That's insanity. That's absolute insanity. But yeah, so here we go. We've got our particle fluids that are being generated from our sphere. So we're dropping these little dots. You can see them. They're just little points, right? They're the little hippie backpackers. That's what they are. That's them right there. So if we look inside of our DOPS network, DOPS being the dynamics operators, DOP, dynamics operators. So now we're working in the world of dynamics. And we look at the solver. So this is the flip solver. This is where all of the wonderful high-level math stuff goes on. And guys like me need to be able to middle-click on these little inputs and see what is it you want from me, silly solver. So I can middle-click on this first input, and it'll say, oh, here is where you can affect the particle velocity. All right? So here's the initial movement of those hippie backpackers with those little yellow arrows on that slide that we saw, the little yellow arrows back and forth between them, where they're determining where they want to go as particles. We can change that. We can plug in any of the pops or particle tools that you may have either seen or used or that you want to use even if you haven't seen them yet. So I can lay down this pop win. Pop, again, P-O-P is particle operators. It refers to anything that you're going to do with particles. So I can just plug that into this input here, one little click. And let's add some wind to our scene. Scoot this back. And now you can see that I've got my fluids going up in y. And the reason for that is because I've got this wind force with a magnitude of 5 pushing up on my particles, right? So it's blowing my particles way up in the y direction. To see it a little bit better, we can go ahead and add a little bit of noise to it. So let's go ahead and just add some noise to those particles. Again, this is all on the particle level. So now we're pushing those particles apart with a little bit of noise and blowing them up in the y direction. We're manipulating that fluid by adjusting its point attributes, if you will, its particle properties. But the cool thing is we also are able to use things like this gravity. So gravity is actually working on the voxel grid. The gravity is pulling down those points after they're being calculated on the grid. We're at 3 minutes. We're at 3 minutes, I'm being told. So yeah, Flip allows you to use both tool sets, both voxel-based tools to sculpt and manipulate your fluids and particle-based tools to sculpt and manipulate your fluids. And that's because it calculates that velocity on the voxel grid. So it all comes down to voxels. All the fluids are still using and able to use the voxel-based tools. So that's why understanding that concept of that 3D grid and what a voxel is and how it works is so fundamental when you get into working with fluids and working inside of DOPS. Okay, that's 3 minutes. Questions? Are there more questions? I can take maybe one or two. Wow, okay. Yes, sir. For the most part, I would say yes, right? They have to be cubic. You can't have a... Are you saying, like, could you have a two-dimensional? No. Or do you mean equal distance in x, y, and z? I mean, you can transform them and stretch them out to all kinds of different things if you want. I think initially, in the initial setup of them, Jonathan actually might know more about this than I would. I'm going to go to you again for that. I think voxels, you do have to have a cubic setup for voxels, right?
But they have the,
Yeah. Right, the division. Right. Yeah. I can't see a benefit to having a non-cube voxel. I mean, once you've calculated the fluid and you've got like a moving wispy thing, if you wanted to stretch it out before you rendered it, yeah, you could take that final calculation and manipulate it and stretch it and bend it, do whatever you want to with it. But the initial calculation is probably going to happen, I would say, for the most part, yeah, in a cubic grid. Oh, look at you. Yeah, that's what I'm after. Yeah. Yep, you can do non-square. Yeah, I don't. Right. I mean, you can start with any shape that you would like. If you want to start with, like, create a tank, instead of a sphere, just make a cube, and then you'd have a tank, kind of with walls. You want to set up some collision walls. You wouldn't even have to. There's default shelf tools for that. Like, you can very easily just come over to the. Where is all that again? Why am I looking up there when I have it right in front of me? So here we can set up all kinds of different pre-built systems for having like a tank of fluid. Like if you want to drop a ball in a tank instead of drop a fluid on the ground, yeah, there's all kinds of pre-builts with the shelf tools that you can get into for building tanks and things like that. But really all you're doing is you're defining a collision border for your fluid and then saying I want the initial shape to be a square, not a box. And then when you hit calculate, you've got a tank of fluid.
Well, more interested, sorry, you were saying about spreadsheets.
Yes.
And how the pixels, or how the particles interact with spreadsheets.
Aha.
That's what I'm trying to get at.
Aha. Yes. I think that's a good call. Come find me and we'll chat about that because, yeah, the way the information goes from the particles onto the grid and then gets calculated and then put back onto the particles, we can talk about that. Come find me afterwards and we can talk about that because that's a fascinating piece of it too. Okay. I think are we giving stuff away now? We got stuff to give away. Who's happy? Who wants stuff? Okay, was that helpful at all? I know it gets a little bit confusing and convoluted kind of at the end, but was the beginning part about understanding voxels and data and information, was that helpful? Yeah? You can say no and throw things at him if you want. All right. We're going to give some stuff away now.